Hi, we will present our CVPR 2023 paper, 3D Human Mesh Estimation from Virtual Markers. Our poster will be presented in person on June 20, 2023. We welcome you to join us at our poster presentation to learn more about our work. Here shows the per frame estimation results on a YouTube video by our method. No temporal cues are used. Our method only focuses on single-person mesh estimation. Therefore, we use an off-the-shelf human detector to detect person first and then estimate 3D mesh for each person using our method. The core of our approach is a novel intermediate representation, named virtual markers, which learns 64 landmark keypoints on the body surface based on the large-scale mocap data, mimicking the effects of physical markers. The virtual markers can be accurately detected from wild images and can reconstruct the intact meshes with realistic shapes by simple interpolation. The pioneer methods such as HMR propose to regress the pose and shape parameters of the SMPL models directly from images. While straightforward, their accuracy is usually limited since the mapping from the image features to the model parameters is highly nonlinear and suffers from image-model misalignment. Some works propose to introduce proxy tasks to get intermediate representations first, hoping to alleviate the learning difficulty. For example, intermediate representations of body skeletons, physical markers, downsampled vertices, body part segmentation masks, IUV images, and so on, have been proposed. However, accurate body shapes are difficult to be recovered from the oversimplified 3D skeletons. The physical markers can be interpreted as a simplified representation of body shape and pose. Although it is very accurate, it is expensive and very few datasets have labels for them, which limit their application to wild images without markers. We are inspired to think whether we can identify a set of landmarks on the mesh as virtual markers, for example elbow and wrist, that can be detected from wild images, and allow us to recover accurate body shapes. The desired virtual markers should satisfy several requirements. First, the number of markers should be much smaller than that of the mesh vertices so that we can efficiently estimate their 3D positions. Second, the markers should capture the mesh topology so that the intact mesh can be accurately regressed from them. Third, the virtual markers have distinguishable visual patterns so that they can be detected from images. To that end, we present a learning algorithm based on archetypal analysis to identify a subset of mesh vertices as the virtual markers that try to satisfy the above requirements to the best extent. Here shows the learned virtual markers, which can coarsely outline the body shape and pose. Ideally, the learned virtual markers could reconstruct the whole mesh with sufficient accuracy, which paves the way for estimating meshes with accurate shapes. On top of the virtual markers, we present a simple yet effective framework for end-to-end 3D human mesh estimation from a single image. It consists of two branches. The first branch uses a volumetric CNN to estimate the 3D positions of the markers, and the second branch reconstructs the full mesh by predicting a coefficient matrix. Then the mesh is reconstructed by simply multiplying the two matrices. Ideally, if we have accurate estimates for all virtual markers, then we can recover the complete mesh by simply multiplying them with a fixed coefficient matrix. However, in practice, some markers may have large estimation errors because they may be occluded in the monocular setting. Note that this happens frequently. For example, the markers in the back will be occluded when a person is facing the camera. As a result, inaccurate marker positions may bring large errors to the final mesh if we directly multiply them with the fixed matrix. Therefore, our solution is to rely more on those accurately detected markers. To that end, we propose to update the coefficient matrix based on the estimation confidence scores of the markers. We train the whole network end-to-end in a supervised way. The overall loss consists of three terms. We define the virtual marker loss as the L1 distance between the predicted 3D virtual markers and the GT virtual marker positions. Note that it is easy to get GT marker labels from GT meshes thanks to our virtual marker learning strategy. We also require that the 3D heat maps have reasonable shapes, therefore, the heat map score at the voxel containing the GT marker position should have the maximum value. We adopt several loss terms to supervise the 3D estimated meshes with additional smoothness terms following previous works. Our approach outperforms the state-of-the-art methods on 3 datasets. In particular, it surpasses the existing methods by a notable margin on the surreal dataset, which has diverse body shapes. Please refer to the paper for more ablation studies. Qualitative results demonstrate the advantage of virtual markers compared to the skeleton representation, which loses the body shape information, so the method pose-2 mesh can only recover mean shapes. In contrast, our approach generates much more accurate mesh estimation results. We show more qualitative results on the natural video inputs. Although our method does not use any temporal information, the estimation results are still smooth and accurate, which demonstrates the strong generalization ability of our approach. Thank you for watching. Our paper and code are available on the website. Welcome to visit the project page for more demos.